Good morning. This is another lesson of algorithmic design. Actually, is the 20th, I think. Uh, Yesterday we had a look to the Tajang algorithm for strongly connect component. We defined strongly connect component, and we saw how to compute them given a direct graph. We investigate the complexity of the Tajang algorithm, and we discover that we are able in linear time with respect to the original graph size, we are able to compute its strongly connected components. Moreover, with respect to the graph of the strongly connected components, so the graph obtained by the original graph by collapsing all the strongly connected components, we also noticed that the Tajang algorithm is able to provide a topological sort of that graph. By performing simply a swap by reversing the output of the algorithm itself. So today we will deal with a really nice problem. Well, the problem is not really interesting by itself, probably, but the algorithm used to solve it, it's really nice, and probably one of my favorite algorithms, and not because it is quite hard to be understood, but in some sense it's just like a symphony. Many factors are involved in the solution, and many different ideas are used to find a way to solve the problem itself. So let's have a look first of all to the problem, and then try to solve it. So the problem is the transitive closure of a graph. What I mean by transitive closure, well, let me go to the slide, otherwise we are done. So the definition of transitive closure is the following one. We want to be able to, given two pairs of nodes of the original graph, to decide whether there is a path from the first one to the second one. Okay? And we want to be able to do this operation for all the pairs of the original graph. Now, the problem is quite similar to what we have already solved, and you may probably already mention the possible solution. So please do it by using the chat if you can figure out a way to solve it. Well, a possible idea would be to, as already said, to use something we already saw, which is BFS. So BFS is an algorithm which enables us to compute the distance between two nodes, but also establish whether the source of BFS can reach another node. So if we apply BFS on each of the nodes of the original graph, we end up with let's say a data structure, a solution, an output, which tell us for each node in the graph which node are reachable from it. Okay. Now, what's the complexity of performing this operation? Well, it really depends on, well, of course, depends on BFS, and as you may remember, the complexity of BFS is big O of cardinality of V plus cardinality of E. So, since the naive solution suggests to apply BFS for each of the on each of the nodes of the graph, we end up with a complexity which is cardinality of V multiplied big O of cardinality of V plus E, which is of course a big O of cardinality of V squared plus cardinality of V multiply cardinality of E. Okay, so this is a kind of upper bound for our quest. So we are trying to find, we want to find an algorithm which is better than using this strategy. This means that any algorithm whose complexity is less than cardinality of v squared or cardinality of v multiplied e is a good solution. So let's see what's going on here, and let's have a look to the matrix formulation of the problem. So if instead of thinking that the matrix as a set of edges and nodes, we move to the matrix representation of the graph, we end up in handling matrices containing 0 and 1s. Okay, so every 0 represents lack of an edge between a node and another node. A 1 represents presence of an edge. So for instance, for this matrix we can see that there is a self loop between 1 and 1 itself. There is an edge between 2 and 1, and so on and so forth. Okay, we already see how to represent a graph by matrices. This is just a kind of recap. So by looking at the matrix representation of the graph, we can easily detect whether a node has a distance 1 from a different node. And this is quite easy to see because you simply have to take the element of the matrix representing the presence of the essence of the corresponding edge. And so in this case, for instance, we know that the distance from 2 from 4 is 1. Okay, so by looking at the matrix representation of the graph, we are able to provide a distance in a kind, a lower distance, which is the distance 1 among the nodes of the graph. Of course, we have to add the 0 along all the main diagonal of the matrix because we are not guaranteed that every node has a self loop, but of course the distance between a node and itself is 0. So just to looking at the matrix representation, we know whether there is a distance of 1 at least among nodes. But if you want to deal with a smaller distance, you also have to add elements along the main diagonal. Now, what about what if we want to deal with a larger distance? So how can we detect whether a node has distance 2 from another node? Well, a node has a distance 2 from another node if there exists an edge moving from that node, so from V to another node. Let's call it Z, and then from Z to W. Okay, so looking at this is of course the very same matrix. So to know whether there is a path going from 4 to 1, we simply have to search for another node, so let's say in this case 2, such that I can move from 4 to 2 along an edge, and then from 2 to 1. And this is enough to guarantee the existence of a path, of course. But from the matrix point of view, this means that we are searching an element, well, we are searching, of course, a column in this matrix, such that the element corresponding to the source row and the column we are searching for is different from 0. And the element from the corresponding row to the column we were searching for to the destination column is again different from 0. In this way we have mapped the problem of searching a path of length 2 from V to W to a problem of searching a path, let's say, on matrices. Now, this is basically equivalent as searching, testing whether the element in the multiplication among these two matrices, which basically are the same, the element in position source destination is greater from 0. Okay, so again, this is not different from 0, is greater than 0 simply because we are dealing with matrices, 0, 1 matrices at the very beginning of the computation, of course, but I mean, you know what I'm meaning here, right? So the idea is to move from searching something in two different matrices, in searching something in one single matrix, which is the multiplication among the two matrices, between the two matrices we were dealing at the beginning. Okay? So this idea, of course, can be pushed over, and so we can find, we can test whether V has a distance smaller or equal than a certain length n from W, so we can test whether W is a distance smaller or equal than V from V, if and only if we the element in position VW on the multiplication, n-time multiplication of A by itself is greater than 0. So if I keep repeating the multiplication of A times A n times, and I look at the element in position VW, I end up with an element equal to 0 every time W is not reachable from V by using a path having distance at most n. Otherwise, I end up in something which is greater than 0. Okay, so again, here we are able to test whether a node can reach another node by using a path having a maximum length, let's say, a bounded length from above, simply by observing the value into a matrix. Okay, this is quite clear. So since every acyclic path has most length, the cardinality of V, so every acyclic path can pass through at most all the nodes on the graph. So if you pass twice on the same nodes, for sure you have moved along a cycle. So if you take into account exclusively a cyclic path, the maximum length of a path along on a graph is for sure the cardinality of the nodes in the graph itself. So when we solve the problem by using the Strassing algorithm, so if we try to compute a at the power of n by using the Strassing algorithm, we land with a solution which has this complexity. So is cardinality of V minus 1. This is due to the fact that we are performing V minus 1 multiplication times the complexity of the Strassing algorithm, which is theta of cardinality of V at the power of logarithm base 2 of 7. Okay? So the idea to solve the problem could be the one of computing the matrix we saw before, so the matrix n at the power of A at the power of n, and then using this matrix as a result. But if we try to perform this operation by using even the Strassing algorithm, which improve the normal matrix-matrix multiplication, the standard naive matrix-matrix multiplication, we end up with a complexity which is even worse than the naive one. Okay, so how can we try to fix this problem. Is it possible to fix this problem? Well, first of all, let me observe one simple things, which is that every pair of nodes in the strongly connected component behaves exactly in the same way. Okay, so from the reachability point of view, all the nodes in the same strongly connected component are the same. Okay, and because of this, a possible way to improve the efficiency of the algorithm could be to build a collapsed version of the original graph, in which every strongly connected component is collapsed to one single node. Okay, that node will represent every node in the strongly connected component of the original graph, and so what's going on here? Let's consider the usual example, the one we saw for BFS, DFS, and to compute the strongly connected component. Of course, you already know these are the strongly connected components of that graph. We saw them during the last lesson, and so we can collapse all of them, so all the strongly connected components, to one single node in this way. Okay. Now, of course, all the internal edges among the nodes of the strongly connected component are removed, while all the nodes moving from one strongly connected component to another strongly connected component are replaced by, of course, an edge. So every edge moving from a strongly connected component to another strongly connected component is represented by another edge. Okay, so this is a different graph with respect to the previous one, of course, but as you see here, we are moving from 3 to 8, so we want to preserve this reachability problem. So we are adding an edge from the strongly connected component containing 3 to the strongly connected component containing 8, and that's how we end up with this graph. Why? So now, what's the complexity of performing this operation? Of course, we know that the complexity is theta of cardinality of V plus cardinality of V. And do we get any advantage from the asymptotic point of view in performing this operation? Well, not really. The point is that you may be already working with a DAG from the very beginning, and so a direct acyclic graph. So in that case, by applying this strategy, so by collapsing the node in a single strongly connected component, you end up with the original graph, basically. So in a DAG, every single node is so every single connect component is a singleton containing it contains exclusively one single node, and then by using this strategy you are not collapsing anything. Okay, so someone is observing that by using this strategy we are preserving information about the reachability property, but we are losing information about the length of the paths. And this is true, but we are not interested in the length of the paths. We are interested in knowing whether from one node we can reach another node. So the point is here is to get return the reachability property, not the distance. Okay. So the original problem, the problem of the transitivity closure, is to decide whether from one node I can reach another node given any pair of nodes in the graph, not to decide what's the distance from one node to another one. Okay. So since we are interested on reachability, by collapsing node, we end up with we end up with a graph which has exactly the same property with respect to the original one, but as already noticed, if we were dealing with directly a cyclic graph, so a DAG, we haven't improved anything, because we end up dealing with a DAG, we end up by collapsing all its strongly connected components, we end up with the very same graph. So why is so intriguing, why is so useful, why it could be so useful performing this operation? Well, let's go back for a while to the well, okay, this is the graph of the collected of the strongly connected component. Of course, we can relabel it by using this nomenclature. So by saying that every time I will mention a node having a cap, a bar over it, I will mean I will mean to deal with the node of the collapsed graph. Okay. So why is so useful to perform this operation? Since we already seen that in DAG is not really important. Well, it's important to apply topological sort. And why? Why is it important to apply topological sort? So once we have decreased, we have collapsed all the strongly connected component, for sure we are dealing with a DAG, and we can apply topological sort, which couldn't be applied on the original graph, because the original graph may contain loops. So to apply topological sort, we need we need to deal with a DAG, and that's why getting the collapsed graph is so important. Now, why applying topological sort is so important? Well, have a look at the adjacency matrix of the collapsed graph. This is the adjacency matrix of a possible collapsed graph. I don't know actually if it is the collapsed graph of this graph, the adjacency matrix of this graph. I guess so, but I'm not sure. Of course, this is the adjacency matrix of that graph, of the collapsed graph, with the addition of the main diagonal, of course. So I've also placed one in every node in the main diagonal to represent the fact that from each node I can reach itself by avoiding, so by a path, a null path, of course. So this new matrix represent the reachability property up to path of length 1. So by applying topological sort, I end up in a situation in which I know how to sort all the nodes. So the first node is not reached by anyone but itself. The second node is not reached by anyone but possibly the first one and the second one. Okay, so what does it mean this from the point of view of the matrix? So if I'm saying that the first node in the topological sort is not reachable by anyone but itself, if we resort the node in the adjacency matrix, we end up in a situation in which the first node in the topological sort has a 1 corresponding to the row corresponding to itself, while all the other nodes are 0. So if I take the column corresponding to the first node in the topological sort, the first cell will contain a 1, then all the other will contain 0. Let's see. So this is basically the very same adjacency matrix, in which I simply resorted all the nodes, so all the row and all the column, according the topological sort. So this is the first node returned by the topological sort, this is the second one, this is the third, this is the fourth, and this is the fifth. Okay? Now how you can see from the slide, uh, the the first node is reachable exclusively by itself. So all the other nodes below him are 0. The second node is possibly reachable by the first one, and for sure is reachable by itself, but is not reachable by anyone else. So all the cells below the main diagonal are equal to 0. And of course this also holds for the third one, the fourth one, and the fifth one. So basically, by applying topological sort to a DAG and resorting the adjacency matrix according to the topological sort, I'm able to get a triangular matrix, an upper triangular matrix. Okay? Which is, I mean, in some sense, strange. Okay? And from a certain point of view may seem to be totally useless. Okay, this is a strange trick, but why this is so important? Why it's so interesting to get an upper triangular matrix? And the point is that oh, by the way, of course, if we apply the Trajan algorithm to compute the strongly connected component, to get, of course, the collapsed graph, the topological sort we got the topological sort for free, because the Trajan algorithm already compute the topological sort. So this step is obtained for free. Now, why is so important to get the upper triangular matrix? Let's go back to the graph theoretical view of the collapsed graph. So the upper triangular matrix, of course, can be represented in this way. So we have a matrix A, which is upper triangular. We have a matrix C, which is unknown. We have another matrix B, which is again upper triangular. And then, of course, in the lower left quadrant, we have a matrix containing exclusively 0. And this is a possible representation for the matrix G. Okay, so this is the graph theoretical representation of the graph G, and this is the adjacency matrix, upper triangular adjacency matrix for G. Now, let's try to understand how the paths among the nodes in G are built. So of course I can move along the edges represented by this matrix. Okay, this part of the matrix will deal with the first node in the topological sort, and this part of the matrix represent edges going from the first part of the nodes in the topological sort to the first part of the nodes in the topological sort. Well, from the first part of the nodes in the topological sort to the first part of the node in the topological sort. So if you take the topological sort and you split them into two parts, the first one, the second one, the submatrix A will exclusively deal with the nodes in the first part of the topological sort. Okay, so it tells you how you can move exclusively on the first part of the topological sort. Now, what about B? Well, B, of course, again will deal exclusively with the last part, with the second part of the nodes in the topological sort, because you know that the source of the edges represented by B are greater than the half of G. Okay, and you end up in nodes which are after the median in the topological sort. Okay, so again, B exclusively represent edges moving from the last nodes to last nodes in the topological sort. Now, what about C, the submatrix C? Well, the submatrix C represents nodes moving from the first nodes in the topological sort to the last node in the topological sort. Okay? So basically, edges represented by C are edges moving from this node to these nodes. This is it. Okay? Now, since the source of the node in C belongs to the first part of the topological sort and the destination of the edges represented in C are in the last part of the topological sort, for sure any path in the graph G can contain at most one edges in C. So there's no way to move from this node back to these nodes. And once I move from this node to these nodes along an edge in C, for sure I cannot take any more another edge in C. So every path in this graph for sure has at most one edge in C. Okay? So basically, if we want to compute the star, so if we want to get the matrix representing all the paths in G, instead of keep repeating bar G multiplied by bar G multiplied by G multiplied by G and so on and so forth for cardinality of V time, we may apply this equation. So we may simply to get that star, so an infinite multiplication of bar G to bar G to bar G and so on and so forward, we can simply compute the star of the submatrix A, the star of the submatrix B, and then once we have these two submatrices, we can apply star of the submatrix A multiplied by C multiplied by the star of the submatrix B. Why? Because again, all the paths in the first part of the topological sort consist exclusively in edges in this part, and this is represented by this submatrix. All the paths touching exclusively nodes in this the last part of the topological sort are represented by this matrix, while all the paths moving from this part to this part are represented by this submatrix. Okay? So the star represents the infinite product, exactly. So it's a way to say I want to multiply bar G times bar G times bar G infinite times. Okay? So the idea is that in some sense exploiting the upper triangularity of the original matrix bar G, we are able to provide an infinite product of bar G by providing an infinite product of two of its submatrices, and moreover we need also to multiply, to perform two matrix multiplication. Now let's have a complete overview of the algorithm. So first of all, and try to figure out what's the complexity of performing all this operation. So we have now a strategy to get the reachability among the nodes of the collapsed graph, because of course this graph will represent the existence of a path among nodes in the collapsed graph, but of course we have to go back to the original graph for sure. But let's have a complete overview of the algorithm. Let's try to figure out the complexity of the algorithm itself. So first of all, we want to this ground, I don't know what it is, but however, first of all we want to compute the strongly connected component of the original algorithm, and this can be done by using the Tajan algorithm, and for sure this takes time, theta of cardinality of V plus cardinality of V. We already know it, we saw it the last time. Then once we have the strongly connected component, we may want, well, for sure we need to build the strongly connected component graph, and this can be done by scanning all the edges in the original graph. So this is the most naive, trivial way to do it. So we simply need to say, okay, the first connect component contains 3, we have an edge from 3 to 4, then we need an edge from the strongly connected component of 3 to the strongly connected component of 4. This is quite easy to do. So once we have performed this operation, we need to perform the topological sort. Of course, if we use the Tajan algorithm, this gets for free. Okay, it's not really needed to repeat this step. So right now we have a complexity which is theta of cardinality of V plus E. Now then we need to compute the G bar star, which is the infinite product of the collapsed graph, of the adjacency matrix of the collapsed graph. So this can be done in time. This is the equation. Why? Let's try to figure out why the equation is this one. Well, to compute G star, we need to compute the star of A, so infinite product of A and the infinite product of B. So we have two recursive calls dealing with half of the original nodes. Moreover, we also have two matrix-matrix multiplication, and if we use the Strassen algorithm, the matrix-matrix multiplication takes time n, where n is the size of the matrix, at the power of logarithm base 2 of 7, of course. So two recursive calls dealing with half of the original matrices, two matrix-matrix multiplication. Now, what's the complexity of this function? So what's the complexity of performing the infinite product of a upper triangular matrix? Well, the complexity of getting the infinite product of upper triangular matrix can be proved to be theta of cardinality of V at the power of logarithm base 2 of 7. Okay? So please try to do it by your own. It's not very tough to get it. It's more or less just like the theorem we got dealing with two recursive call involving alpha n and beta n, if you remember. Okay, so it's quite easy. You end up in dealing with the geometric series, and the series at the end can be solved in a constant time. Okay, so once we have compute the infinite product of over bar G, we can extend the transitive closure of that matrix to G, and this can be easily done simply by going back from the strongly connected component, from the nodes in the strongly connected component collapse graph to the original strongly connected component. So every node reachable from the on the collapse graph, every node in the strongly connected component in a strongly connected component will be able to reach every nodes reachable in the collapsed graph corresponding to the to that strongly connected component. Okay, so you simply have to look at the overbar G to get the reachability property for G, and this of course deal can be done in time quadratic with respect to the original matrix. Why? Because if we want to represent this reachability by using a matrix, a square matrix, of course we need to fill the matrix by using zeros and ones. Okay. What do you mean by infinite product exactly? So there is a question from one of your colleague. What do you mean by infinite product exactly? We mean to stop after cardinality of the product? Then, well, going back to this stuff, okay? So this procedure is a recursive procedure which will end up when each when the matrix when we will deal with matrices whose size is 1, and this is enough. Okay, this is the point. At the end you end up in dealing with something which is exactly what you want. Okay, now so let's try to sum up all the complexities in this schema. So Tajan algorithm, theta of cardinality of V plus cardinality of V. Build the strongly connected component takes time theta of E. The topological sort is obtained for free. The computing the overcap G star takes time theta of cardinality of V at the power of logarithm base 2 of 7. And understanding the transitive closure, as soon if you have yeah, exactly, we have exclusively 0 1. So if you have this I lost myself. So oh yeah, and the last part is simply required to perform this operation, so to refill everything. So the complexity, the overall complexity of asymptotic, the overall asymptotic complexity for this algorithm is this one. So please remember that logarithm base 2 of 7 is greater than 2. Okay, so this is the complexity, which is quite better, which is the complexity of the previous of this algorithm, which is better from a certain point of view, better than the naive one. Why? Because we are not multiplying anymore the cardinality of V to the cardinality of V. Okay, so if you are dealing with a dense graph, let's say, this algorithm is much better than the previous one, of course. However, if you are dealing with a graph which is not dense, so let me go to the naive complexity, this one. Okay, so if you are dealing with a graph which is not dense, so number of edges are small, of course this algorithm is much better than the one we just obtained. Why? Because this is big O of cardinality of V square, while our algorithm is so this algorithm transitivity closure is cardinality of V at the power of logarithm base 2 of 7. However, of course, if your edges are more uh, are more uh, than V, of course, this algorithm could be quite efficient. Okay. So if your graph is not sparse, this algorithm is much better than the naive one. This is all I want to tell you about transitive closure. As you see, this is a quite strange algorithm. The problem is not tough by itself. It's easy to be explained. It's in some sense trivial, let's say, because we can provide a naive algorithm which is not that bad in some cases. However, I really like this algorithm because it's as I said at the very beginning of this lesson, it's just like a symphony. In some sense, you are to solve it, you are using many different sub algorithms and many different sub ideas. So first of all, you need to get the idea. You need to get the idea to uh, to collapse all the nodes. And at the very beginning, I mean, this idea seems to be totally useless. Because as I said before, if you are dealing with a DAG, collapsing all the nodes does not give you any improvement from the asymptotic point of view. And then you need to have the intuition that by using topological sort on a DAG, you end up with an upper triangular matrix. And again, this alone is not really interesting. But then, if you are able to understand that by dealing with an upper triangular matrix, you are able to decompose all the paths in the graph into path going from the first part of the topological sort, the first part of the node in the topological sort, to the second part of the topological sort, moving along edges between these two groups only once, then you are able to provide this matrix. And this is, I mean, really surprising if you think at the beginning. Okay. And moreover, also the fact that we are able to multiply things you are able to multiply matrices better by using an algorithm which is better than the naive one is really important. So here we are using so many ingredients and to get the result, and all these ingredients fits exactly in the right place. So this is I really like it because of this. Okay, so here we are using Tarzan, we are using topological sort, we are using the Strassen algorithm, we are using the idea of resorting all the nodes in the adjacency matrix by using the topological sort. We are using the idea of dealing with a upper triangular matrix. So this is really, I mean, appealing from my point of view. And this is all I want to tell you about transitivity closure and about, let's say, standard graph. Okay. Now let me move to another topic then. But first of all, I want to change. Okay, give me a second. Give me just a second to load all the slides. Here we are. So during the last lessons we saw the notion of graph, and we saw algorithm on graph. We were dealing with the breadth first, we were dealing with DFS, we were dealing with topological sort, strongly connect components, the Tarjan algorithm to get them, and the transitivity closure of the graph. Now, this is quite interesting. We learned a lot, but I mean, dealing with the standard graph, let's say, is interesting, but not that useful. I mean, we can do much more than that. So think to, for instance, to a network of street, and so a street network, and in a street network, of course, you may have local street, you may have highway, you may have I don't know, regional street, and so on and so forth. So the time required to perform to go along all these streets, of course, depends on many factors, but for sure the local streets are usually have usually a lower speed with respect to the highways. Okay, so if you want to represent in some sense a street network by using a graph, you need a way to label each node, each edge in the graph by using numbers. For instance, to represent the time required to go along the edge. Okay. So the idea here is, let me repeat this example. Let's assume we want to represent a street network by using a graph. I mean, there will be edges in which the time required to go through the edge, so go through the street, is small, and there will be edges in which the time required to go through the edge is high. So we need a way to label all the edges according to some numbers that will represent, for instance, as an example, the time required to go along these edges. And that's why dealing exclusively with graph, standard graph, is not enough to perform many things, to model many things, such among these things, for instance, a street network. So we need a way, as I said, to label the edge, and this can be done by using what is called weighted graph. So let me move to the slides here. So what's a weighted graph? A weighted graph. Well, a weighted graph is just a tuple, VEW. Well, VE is as usual a directed or undirected graph, as we are used to handle. And W is simply a function mapping edge into weights. So it's a labeling function, basically. As you see here, we moved from the standard graph situation. This is a graph as we are used to this case, in which every edge is labeled by using a number. Okay, and this is it. So now we can, by using this new notion of weighted graph, we can change also. We may also need to change the notion of length of the path. So in the standard graph, the length of the path is the number of edges required, the number of edges involved in the path itself. While in the weighted graph, the length of the path is the sum of all the labels involved in the path itself. So, for instance, if I want to know the length of the path from E to B, well, the length of the path from E to B moving along A is 5.3 plus 4, so 9.3. Okay, this is clear. So how can we represent graph? As usual, we have two main ways. The first one is adjacency list, as already said for sparse graph. But in the adjacency list, we not only need to specify which nodes are reachable by using one single edge, we are also required to specify the value of the labels. So in this case, for instance, we are moving from 1 to 4, 1 to 4, along a path whose weight is 8. Okay, and again, here in this case, we are moving from 1 to 2, along a path whose weight is 4. So from 1 to 2, and the weight of the edge is 4. And this is it. So this is more or less like just like what we saw for the, let's say, standard graph, so unweighted graph. But in this case, we need also to specify the weight of every single edge. Now, what about the adjacency matrix? Well, the adjacency matrix, again, usually used for dense graph. It's almost as we already saw, but we need to update in some sense this data structure in the following way. First of all, since we may have a 0 labeling an edge, we need to provide a different value for the absence of an edge, and this is done by using, for instance, nil, here represented by n. Okay, so when you in your adjacency matrix you find a nil or an n, you are saying that basically there is no edge between the two nodes involved. Okay, otherwise you may find a value, and that value is the label, so is the weight of the edge among the two nodes. So for instance, in this case, let me go on. The first row we represent all the edges moving from 1. We have two edges in this case. The first one goes from 1 to 2 and is labeled 4. So in row 1, column 2, we have a value which is 4, and in column 1, row 1, column 4, which represent the edge moving from 1 to 4, we have a 6, which is the label of the edge. Okay, so quite easy. And in the remaining part of the row, of course, we have an n, which is in this case a standard way to say, look, we don't have any value for that. Of course, you may choose a different way to represent the absence of the node. It's up to you to decide your encoding. I mean, this could be the largest number representable by an integer. This could be 0, as long as you don't have edges labeled by 0, or whatever you want. I mean, okay, it's just up to you. This is it. So the other part of the matrix is more or less similar to what we are seeing up to now. Now, what can we do once we have defined the graph in this way? So, what we have defined weighted graph. A possible question which may arise is the question of deciding the shortest path from one single node. So the problem here is the single source shortest path problem. And the idea is we want to compute all the shortest path from a single source. So how can we solve the problem? Well, the point is that actually we already solved some similar problem, a similar problem on unweighted graph, so on standard graph, let's say. So if you remember, we solved it by using BFS. Okay. So the idea is that was to use BFS, breadth first search, to get to label in some sense each node with its distance from the source. Moreover, BFS will also returns a tree, which is the tree of the shortest path from the source. Okay, so the single source shortest path on unweighted graph has been resolved by BFS. Here we are asking to solve the problem on weighted graph, which is a slightly different problem. Okay, so we in some sense we increase the complexity of the data structure we are dealing with, and we want to solve exactly the same problem we solved by using BFS. So can we adapt BFS to solve the single source shortest path problem? Let's see. So first of all, let me recap just for a second what we did with BFS, just to understand what's going on here. In BFS we had three kind of nodes: white, gray, and black. Okay, white nodes are not that hasn't been discovered yet by the procedure. Gray nodes are nodes that have been discovered, but some of their neighbors are not been discovered yet, and they are not finished. So if you remember, BFS use a queue, and all the nodes in the queue are gray. And finally, black nodes, which are nodes that have been discovered and was discovered, and moreover, all the neighbors was also discovered. Okay, and in BFS, the search exclusively evolved from gray nodes. So the idea is that from a gray node, I discover new nodes. That nodes were pushed into the queue, and then every time I need to evolve to search for new nodes, I extract an element from the queue, and I move to the neighbor already discovered neighbor of the element removed from the queue, and that element was gray node. Okay, so let's have an example, a working example to try to understand what's going on. Again, this is an example on BFS. So is an example on not weighted, so unweighted graph. Okay. Here every node is labeled upside by the name of the node, just to simplify my talk. And inside its node you find the distance from the source. So the first step is to select the source, and let's say this is the source of our search. If we select the node number 1 as source, its distance from the source of course is 0, and the source is gray colored and placed inside a queue. Okay, then we extract 1 from the queue, and we search for all its neighbors which haven't been discovered yet. So we search first, let's say we have two possible choices. We may choose 3 or 2 as first neighbor of 1. Let's say 2, it doesn't change more or less anything. So again, 2 once 2 is discovered, we can set its distance from 0 and then place it into the queue. And of course we may go to 3. So we haven't finished with all the neighbors 1. We need to go to the node number 3. Again, its distance from the source is 1 because it's a neighbor of the source. And once this is discovered, all the neighbors of 1 are either gray or black. So 1 is no more needed to perform BFS. So its role in the play has ended. So we can black color it and forget its existence, at least as far as the computation of BFS concern. Okay. Now let's move on. Okay, now we move from this node. Now the queue tells me that I need to deal with number 2, and so I move from 2 to 5 because it's the only neighbor, unvisited neighbor of 2, and so 5 becomes gray. Its distance from the source is the distance of 2 from the source plus 1, and since no more nodes are white nodes are reachable from 1, directly reachable from 1, 2 becomes black, and 5 of course entering the queue. Now what I deal with 3, which is in the first part of the queue. I can move to either to 8 or 9. I decide to go to 9 first, just because my taste, of course. I mean, it's not really relevant. The distance of 2 from the source should be the distance of 9 from the source should be 2. Why? Because the distance of 3 from the source was 1. So this is just discovered. This has been just discovered. So its distance should be 2 from the source. And now 3 couldn't be deleted simply because it's already have a white neighbor. So we need to select the other white neighbor. Again, we are labeling the 8 as distance 2 simply because the distance of 3 was 1, and now no more white nodes are directly reachable from 3. So this node number 3 can be black colored and is no more relevant for the BFS from the BFS point of view, and so on and so forward. So you know what's going on here. As you see, we are always dealing with gray nodes. So the really important the node really important for the evolution of BFS visit are the gray nodes, not the black one, not the white one. Okay. And okay, you can go on. This is the code, we already saw it. I mean, you can simply have a look at it, but we already saw it during the previous lesson. So let's try to, now we understood how BFS work, and let's try to upgrade BFS to deal with weight. So we understand that in updating the value of white node, we simply place the value. We set the distance of the node, or just discovered node, to the distance of the node from which we discover it plus 1. Why? Because every edge the value of every edge is 1 basically. Okay, so a possible way to improve, to upgrade BFS to deal with weights could be to set the distance of just discovered node to the distance of gray node plus the weight we move along to reach the just discovered node. Okay, but unfortunately it doesn't work. So this idea to take BFS and upgrade it simply by setting the distance of a node, looking at the gray node from which I reach it, and add to that distance the weight of the edge along which I reach the new node, doesn't work. Why? Well, first of all, try to understand why BFS worked. And the idea that and BFS worked because of this lemma that we saw it. So along the computation of BFS, we are dealing with a queue, which is the queue of the gray nodes. Okay, and this queue has the property that it is sorted with respect to the distance. So the smaller index corresponds to a node. The smaller is the distance from the source. But we have also the property that the first one, the distance of the first one plus 1 is for sure greater or equal to the distance of the last one. Okay, so all the distances of the gray nodes are included, belongs to an interval which has at most length 2. Okay, so when we extract an element from the beginning from the initial part of the queue and we increase it by 1, we are guaranteed that distance, so the new distance we assign to the just discovered value is for sure smaller or equal than the distance of all the other nodes. Okay, let's try to see what's going on. Let me move to the table. So we have a queue. Let me draw exclusively gray nodes, and this is a white nodes. Okay, so this is a gray nodes, gray, and this is a white node. Okay, and here we have edges moving from all these nodes. Let me call this A, this B, and this C, and this will be D. Okay, now in our queue we will have, since A, B, and C are gray nodes, for sure they will be included in queue. And let me set an order. This is just for the example. Let me set an order. Let's say they are in this order. Okay, now since they are in this order, since they are in this order, we know that the distance from the source of A is smaller or equal than the distance from the source of D, which is smaller or equal than the distance of the source from C. Okay. So now, if I select, so since A is at the beginning of the queue, the distance at which I can find D is, so D will be set to let me go back. So the distance from the source of D will be set to the distance from the source of A plus 1. Okay, Now, because of this and because of this property, we are guaranteed that any possible path to D should be greater than the path we have just discovered by moving from A. Why? Let's assume we instead of A we take B as predecessor of D in the path from the source to D. Well, in that case, the distance would be the distance of D would be D plus 1. But because of this property, for sure this is greater or equal than A plus 1. So by selecting the first element in the queue, we are guaranteed to build the shortest path. Okay? So let's say if I'm able from a gray node, if I'm able to move from a gray node and reach D, when for sure the smallest, so the first element in the queue which is able to reach D is the best choice to get the shortest path. And once we have just discovered it, we are guaranteed that this is the shortest path. And this is due to the fact that all the other paths moving from B, C, and so on so forward must add at least an edge whose length is 1. Okay, it's not possible to have anything but 1 here. We don't need to check whether there is whether the length of the edge, the weight of the edge is smaller than 1, because we were dealing, in using BFS, we were dealing with unweighted graph. Okay, so using the queue is enough to get was enough to get the shortest path. Okay. However, if we move from the unweighted graph situation to weighted graph situation, this property is no more true. Okay. So it could be the case that one of the grade nodes has an edge. So not the first one, but one of the grade nodes which are in the queue has a weight for the edge moving from it to the node which is smaller than 1. Okay? And so it doesn't work. So it doesn't work in this way. So it could be the case that the first element in the queue added with the weight moving from it to the node we want to reach, so D, is greater than the weight, the distance of another node in the queue plus the weight of the edge moving from that node to another node. So let's see an example. For instance, this is let's say a kind of trial to use BFS on weighted graph. So here we have a situation in which we have a black node, so already completed, 2 nodes in the queue, and the other nodes are undiscovered nodes. Okay, and this is the queue of the BFS visit. So the first element in the queue is 2, and because it's the first element, we may try to extract this node from the queue as a candidate to expand our shortest path. But if we do it, we end up in selecting this node because it's the only one reachable for 2, and we label 6 as reachable from 1 in 16 steps. Okay, so the distance from 1 of 6 is 16 if we try to apply the BFS like visit. However, this is not really wanted, it's not really true, because if instead of selecting this node I select this one as first one, so if I avoid to have a look at the queue and try to expand this path, I end up in discovering that 6 that the distance from 1 to 6 is 5 plus 2 plus 1 plus 3, which is 11, which is far less than 16. Okay, as a matter of fact, let's have a look here. If I take the distance from 2, which is 1, and I sum up this edge, the weight of this edge, and I take the distance of this node from the source, and I sum up the weight of this edge, well, I discover that the path moving from 3 is smaller than the path moving from 2. Okay, so in some sense I need to take care of this situation, and I need to expand exclusively the path which is the shortest one among all the possible expansion of the path. Okay, so let me just provide a possible intuition of how we can solve this problem. So the idea in this case to solve the problem is to avoid to enqueue non-discovered nodes. So to avoid to enqueue discovered nodes, and to enqueue exclusively not discovered nodes. Okay, and to pre-label all these nodes with a candidate distance. We already did in some sense by setting all the distance to infinity. So at the very beginning of the computation, the candidate distance of all the nodes by the source will be infinity. But as soon as the let me try to answer some of the questions I just received. What do you mean by query? Here we don't consider anymore the node to self path as always present. We waited to now. Oh yes. One of your colleagues is asking whether in weighted graph we may have self loops, and yes, we may have or not have self loop, of course. If we have self loops, we may label self loops. Well, we should label it by using weights. Okay, and if you wonder if weighted so if you wonder whether self loop is necessary to check the reachability, no, it's not needed, but it wasn't needed also in unweighted graph, so this is enough. Other question: the shortest path, single source shortest path problem implies that we need to find the shortest path with the minimum cost, I think too. Well, the shortest path, what I mean by shortest path, I mean since the length of, well, the shortest path is the path whose length is the smallest one. We change the meaning of the length of the path, and we said that the length of the path is the sum of all the weights along the path. So it's not, this is, I mean, it's straightforward, the definition of single source shortest path. So the shortest path is the path whose weight is minimum. We don't need to add anything. Can we just ignore the weights? No, we cannot. I just said that it's not possible to avoid to consider the weights, because otherwise you end up with a mess. I just show you in this case If we avoid the weights, we end up in discovering that the shortest path is, well, if we try to apply BFS to this graph, for instance, we discover we get an error, because we end up in a situation in which 6 is labeled as distance, so is labeled as having a distance 16 from the source, which is not the case, because if I move along this path, so the lowest one, let's say, I may observe that the distance along this path is 11. Okay, so if your question is to decide the reachability, can we just ignore the weights, the answer is yes. If your question is has sense this problem, well, yes, has sense, because I said if you are dealing with a street network and you want to find the shortest path, which is the path will take you the smallest amount of time from Trieste to Milan, for instance, just to make an example. For sure you need to take care of the speed limit, and the speed limit may be one of the possible way to label your graph. Okay, so, well, the opposite, the time required to move along one street could be the possible way in which you label the graph. So this problem is of course interesting from that point of view. So any idea to solve the problem? Well, as I said, to solve the problem we may try to avoid to enqueue just discover node, and enqueue not discover node. And not discover node must be pre-labeled in some sense with a candidate distance. At the beginning, the candidate distance would be infinity for all the nodes. Then we select a source. The candidate distance of that source would be set to 0. And then we know that we must expand node from that node, expand paths from that node. Then by selecting that node as finishing that node and saying, okay, that node has distance 0, we can move and selecting it as the most interesting to evolve. We need to update all the distances from all the candidate distances for all the nodes reachable with just one step from that node. And then among all the nodes whose candidate distance is not finalized, we must select the one with the smallest candidate distance. And for sure, every possible path reaching it should, but the one we have just selected, well, all the path moving from the source up to that node for sure has a length which is greater or equal to the one we have set. So so that distance could be finalized, and that's all. So let's have an example. For instance, in this example, we have BFS visit, as I said. So this is again a recap of what we saw before. Here we are trying to apply BFS visit on this graph, and we move from 0 to 2 and from 1 to 2 and to 3. They are on the queue. So we may try to update. No, this is sorry, this is the new version, so the version in which we try to update the candidate. Okay, so by crossing this edge we may update the candidate distance of this node, that would be 16 according to this path, while the candidate distance of this node will be 7 according this path, and at each step we select the minimal candidate, so the candidate whose distance is minimal, we extract it and we finalize it. Okay, and of course we need to update the outgoing neighbors of that node. So for instance, in this case we need to update, we need to select among all the white nodes the best candidate to be finalized, and this is 7. Why? Because the distance of the other nodes, the candidate distance of the other nodes are greater than 7. So for sure the distance of this node, so this distance of 4, couldn't be decreased by looking at the other nodes, because the other nodes are being already have already a candidate distance which is greater than 7. So the shortest path moving from 1 to 4 for sure has at least distance 7, and this is also the shortest non-finalized node. This is the node whose unfinalized node is this is the node whose distance from the source is minimal among the unfinalized node. So for sure this is the correct distance from the source, and we can remove it from the queue. Okay, now now 2 nodes are left. Again we need to choose. Please notice I have updated this node, the candidate distance on this node, on node number 5, according the distance of node number 4, increasing by 1 because the edge from 4 to 5 has weight 1. Now now again we need to choose the smallest candidate distance among the unfinalized node, not finalized node, and in this case the smallest one is this one, so it's the node number 5. So we take node number 5, we finalize it, and by finalize it we can update the candidate distance of all its neighbors. In particular, it only has one neighbor, which is 6, and so before taking 5 as a finalized node, we have a distance of 6 as 16. Now we finalize it, and so we can update the distance of 6 according to the distance of 5, which is 8, plus the weight of the edge moving from 5 to 6, and we end up with a candidate distance which is 11, which is smaller than the previous one, so we can update it. Okay, so the idea is to avoid to enqueue just discover node, and instead enqueue not discover node, not yet discovered in some sense. Okay, and not yet finalized yet, and we pre-label them by setting infinite distance, and as soon as they are reached we update their candidate distance. Okay, once they are the smallest among all the possible candidate distance, we are guaranteed that that distance is the correct one, because any possible path moving to it along non-finalized node for sure would be greater than the one we have just discovered, and that's it. So the idea is to avoid to use avoid to use a queue, and instead using a priority queue. And this priority queue will be a priority queue with respect to the candidate distance. Okay, We will deal with all the details during the next lesson. That will be on Thursday, I think. So this is enough for today. I think you have so many things to understand up to now. But the idea, let me repeat just once more. The idea is to move the attention from the just discovered node to the undiscovered node. Okay, and we don't want to extend in some sense the path from the just discovered node. We want to extend the path from the node whose candidate distance is the smallest one. Okay, so this is enough for today. Let me just say give you one more pieces of information, which is related to the exam. This is usually really exciting news for you as student. Of course, I mean, the situation is the one you already know. I think that is really not possible to have written exams. So all the exams for this course will be oral exams. In the very first part of the year, we will have, so on the summer session of the exams, we will have oral exam by using Teams, or I mean, depends on what you prefer. Though probably we are forced to use Teams. However, we will be online. Okay. So don't worry, we are not going to have any written exams for algorithmic design. We will also only exclusively have oral exams together with homework done. Okay. So this is enough for today. Please let me know if you understand what I said, if everything is clear. Make some comments, and see you soon then. Thank you for your attention. Bye.